My name's Craig Stevens. I'm an applications engineer / field engineer for Intercad, and I'm based in Adelaide. I've had over 25 years experience in CAD and about 20 years experience with SolidWorks this year. I've got SolidWorks certification as an expert and also in the data management areas for PDM Professional. And I've been building computer systems as a sideline just for myself, for personal use for CAD and for personal use for about 20 years as well. Let's move into the content of today's presentation. So just talk about the series that we're going to look at over the next year. So part one today is hardware recommendations and tweaks. The second part and the third parts will be covering off looking more closely at parts and sub-assemblies and also drawings and how we can improve performance in those areas. Then for part four we'll cover off some tools and tips and anything else that that we haven't covered in the first three parts, and hopefully by that time we'll be out of the 2018 beta program, and we might have some more information about some improvements that will be coming to handle large assemblies for that particular release. Okay, so the agenda for today, we're going to start looking at SolidWorks hardware general recommendations. Then we'll have a look at the actual hardware architecture. So what does your hardware look like underneath the box or in the laptop? Then we'll move into a component breakdown, looking at the individual components and how some of those things can affect SolidWorks operation. And then to finish off, we'll have a look at operating system and network and virtual environments, which are not really, strictly speaking, hardware, but they sort of fall into this category. So we'll have a look at those. So looking at SolidWorks general recommendations, these are minimum requirements shown here for SolidWorks. I've taken them directly from the system requirements page. The links are shown below. And there's a sub-link there from the hardware page to system requirements. These requirements apply as a general rule across all SolidWorks system requirements, but if you want more detail, please have a look at those sub-links there for more info. Some of the PDM system requirements aren't as stringent, so for the viewers and the clients, they may only need sort of 4 or 5 gigs in terms of RAM. But obviously, yeah, please have a look at those links for more details. In terms of RAM, SolidWorks is specifying 8 gigabytes as a minimum. I would suggest that you probably need more if you're into large assembly modelling, and we'll talk about a bit more about that. Graphics cards, SolidWorks are suggesting certified only, and I'll reiterate that a little bit later on. The CPU, or Central Processing Unit, they support both Intel or AMD with an SSE2 instruction set on the chip. That's a bit of a broad specification. SSE2 was introduced on the Pentium 4 chips back in 2001, so I'd probably say that if you're running large assemblies, that you probably want something a bit better than a Pentium 4. Alright, we'll give more detail on the CPUs in the breakdown. And 64-bit operating systems, obviously after the SolidWorks 2014 release, that was the last 32-bit release. 2015 onwards is 64-bit only, and again, if you're doing large assembly modelling, I wouldn't be using 32-bit, I'd be definitely be using 64-bit operating system going forward. Alright, so let's move on and have a look at the actual hardware architecture. What I've got here on the screen is just a SolidWorks render from of a system board that I grabbed off 3D Content Central. It's an empty system board, and I've just indicated on there with a few notes where the major components sit. The CPU, obviously where all the major calculations are executed. Sometimes this might get referred to as the North Bridge. The RAM, or random access memory, the chips sit on the board there. SolidWorks is RAM resident, and that's where the files exist when we're working with them. The PCI bus is where the graphics cards or network cards sit. They communicate via this bus back to the CPU. We've got serial ATA connectors on the board, and that's generally where your hard disk drives or optical drives connect back into the system. Older boards might have parallel ATA or other type connectors on there, but generally with the more modern systems they're not present. The South Bridge is a secondary chip, and I probably wanted to show the board more for this than any other thing, because this chip is responsible for controlling the communications of the peripherals. So anything that's coming through the PCI bus is going to go through that South Bridge into the central processing unit. And cheaper boards will have cheaper specs on those South Bridges, and consequently might be responsible for a bottleneck. Okay, and then obviously you've got some peripheral connectors on the board as well, but most of those won't have an impact on load assembly, so we won't talk about those too much. Let's get into the CPU. I guess the key thing with the central processing unit is the clock speed, and generally speaking, with a lot of dedicated CAD systems, they're using overclocking now, and this helps us to improve rebuild times in SolidWorks. What is the clock speed? It's the chip specification for the speed of the central processing unit. Why would we overclock? We get better performance, that's why we would do it, and it's probably more important for large assembly modelling for SolidWorks, because the faster that chip's running, the faster we'll get rebuilding on the feature manager design tree. What's the downside of overclocking? Obviously you're putting increased voltage across the CPU, and it could cause it could cause extra heat to be dissipated through the CPU, and then ultimately it could cause it to fail. If you have a look at some of the overclocking world records, they're indicating overclocking speeds between the 6 and 8 gigahertz range. They're not really stable at those speeds. These guys are overclocking purely to say that they can overclock at those speeds. For safety's sake, most overclocking occurs up to about 4.5 gigahertz on the current generations of CPUs. So looking on the right hand side there at that CPU world records, the latest chips are the Skylake and the Kaby Lake processors. Some of the earlier versions of the Core i7, so the Nehalem and Sandy Bridge, may not overclock to those speeds, but anywhere from about 3.5 up to about 4.5 gigahertz in the current range. You can use the CPU-Z utility to check your core speeds. If I just bring that up on the screen, it's just a small utility there, and it basically allows us to see real time what our clocks are doing on the processor. You can see mine sitting at about a 3200 megahertz at the moment, but if I actually bring up the system specs for this particular machine, you'll see that it's actually specified at 2.6 gigahertz. So it is it's being overclocked at the moment, and that just helps us in SolidWorks. All right, the CPU pass marks that I'm showing here as well. If you have a look at the CPU benchmark website, that'll just give you an indication of what the base speed should be for any particular chip, and you should be able to find your chip on there. It's constantly updated, so you can check out what you've got there and what you should be getting, and what you might be able to get as well. You can also get your IT to check it if you don't have access to these sorts of tools. They might be able to tell you what that is. One other thing to mention here is Intel Turbo Boost. This is a technology which is available on the core chips, and what it effectively does is it overclocks your processor for you when you need it, and it's pretty much seamless. You wouldn't notice anything different in the background unless you were monitoring it with something like the CPU-Z utility. It's operating system controlled, so the operating system will tell the chip when it needs that extra boost, and it will do it for you. If you have a look at the chip specs for your specific chip, it'll tell you whether it's got the turbo boost capability, and whether it's going to overclock and help you in that respect. But the chips can be overclocked independently of that as well. Just one final note on that. I have a personal preference for Intel chips over the AMD ones, simply because AMD chips typically run hotter to start with. I'd probably say 99% of our customer base are using Intel anyway, so just thought I'd mention that. Continuing on with the CPUs, SolidWorks does have multi-core or multi-CPU support. There are some low-level operations in SolidWorks in the algorithms which use multi-threading, so Boolean, silhouettes, line generations, mass properties and body checking are all handled at the low level by SolidWorks modeling algorithms. These operations become multi-threaded in SolidWorks operations like the cut, extrude or emboss. However, SolidWorks doesn't use low-level modeling algorithms on a one-to-one basis, and therefore it's a bit difficult to ascertain the overall effect. But where we do see those or multi-core being used is in open. So if we're opening parts, it can open multi-threaded, and for assemblies as well. Save operations, import, export, calculating high-quality drawing views. Obviously there are multiple drawing views on a sheet. It can calculate the high quality on that using multi-threading. Similarly for rendering threads in high quality, and also for PhotoView 360, it can render multiple threads at the same time. Simulation also uses it, and particularly for FlowSim, multi-core is used. But more specifically in this case, or for large assemblies, assembly loading can use multi-threading and multi-core support. And we'll probably talk a little bit more about that when we go into the parts and sub-assemblies in the second part in the series. Plastics also uses it, and parallel tessellation. And we'll look at parallel tessellation in a little bit more depth. What this does is it reduces the time it takes to regenerate the graphics display of large assemblies. The components are not processed individually. All of the bodies are gathered together, and they're retessellated at the same time. And so we have parallel tessellation of a longer list of bodies in the assembly. Now, to take advantage of this, in SolidWorks 2016 and 2017, in the document properties for that top level assembly, you would have a look at your image quality settings. You would modify that down to a low setting here, and then you would apply to all reference part documents, and it would change this shaded and draft quality resolution tolerance on all of the components. And when it does, by doing that, it will take advantage of this parallel tessellation, resulting in better performance in your large assemblies. Another tool we have in large assembly modelling is verification on rebuild. It's available for all parts and assemblies, but it's probably wise to turn this off in large assemblies. When it is off, the software checks every new or changed feature against any adjacent faces and edges. When it's on, it checks changed features against all existing faces and edges, not just the adjacent ones, and it's very CPU intensive. So at the large assembly model, it's probably best to turn it off. Really great for checking self-intersection on sheet metal parts at the part level, but not for large assemblies. Just to wrap up on the CPUs, high clock rates are desirable, so 3+ gigahertz on the chip. When you're getting down to 1.8 or 2.0 gigahertz, SolidWorks is probably going to start to struggle a little bit, particularly at the large assembly end of modelling. I'd probably always recommend using Core i7s. I've seen a few people with Core i5s, but at large assembly model you really need to be using the i7 to get the extra high clock speeds and to take advantage of overclocking as well. And again, it's giving us that faster solving of the feature manager design tree. Xeon cores, Xeon chips, offer more cores, which gives you the benefit of multi-threading, etc. But again, they tend to have, at base level, lower clock speeds than the Core i7. So if you're solely doing large assembly modelling and you're not interested in rendering and simulation, then Core i7 is probably going to be better than the Xeon chips. CPU used in the tessellation of graphics. Obviously we talked about that parallel tessellation, but when we're talking about tessellation of the graphics, before you can actually start using your large assembly model, you might see generating graphics at the bottom of the screen in SolidWorks, just below that motion study tab. Whilst it's loading everything up, until that's completed, you won't be able to use your model. So the faster you can tessellate those graphics, the faster you'll get into working with your model. So yeah, I guess just the interesting point there is the CPU is actually what's used to prepare the graphics during the loading process, not the video card. The video card kicks in once it's generated those graphics, and then it's used in the manipulation of the model on screen, so zoom, pan, rotate, etc. Alright, moving on to RAM in a bit more detail. SolidWorks has that minimum recommendation of 8 gigabytes for 2017. You can kind of read into that what you will. Obviously for large assemblies, the more the better. My discussions with SolidWorks technical support would seem that moving much beyond 32 gigabytes at this time is probably slightly overkill. So that's probably where I would say that the maximum level is at this stage for desktops and laptops. But 16 gigabytes is probably most common. But certainly SolidWorks will use as much memory as it can get its hands on, so if you're willing to fork out the extra expense for 32 gigs, then all well and good. I guess the issue is if you don't have enough RAM, Windows is going to revert to using virtual memory on the hard disk drive, and that's going to be slow, really slow, because hard disk drives are much slower than the RAM. SolidWorks does recommend that users specify that their virtual memory be at least 3 times the amount of their RAM. Where do you specify that? Well, if you right-click on your computer and get into the system dialog, and I'm currently using Windows 7. This might look different on Windows 8 or Windows 10. If we go to the advanced system settings on the left hand side there, we'll bring up the system properties, and then we need to go into the performance area here and click on the settings button, and then click on the advanced tab, and then under the advanced tab you'll see virtual memory, and if I click on the change button there, you will see an option here. Mine's currently set for SOLIDWORKS to manage the paging file size, but you can deactivate that, and then it will give you the options to set custom sizings for that page file data. Okay, so if you were finding that you were getting into virtual memory and you didn't have enough, then you could change those options there. With systems that have got 4 gigs or less, for probably SOLIDWORKS 2014 onwards, you're probably likely going to see instability with low system RAM on the system for large assembly modelling. ECC, or error correcting code memory, can detect and correct most kinds of internal data corruption when data requires 100% accuracy. This is when you need to be using ECC RAM. You might see this on Xeon based systems. They support the use of ECC RAM, and vendors like Dell and HP like to marry that ECC up with their Xeon chips. But typically it's really only used when you're dealing with scientific data. So if you're building a large Hadron Collider and you're analysing where your Higgs boson particles are, then that's probably where you're going to use that. It's not a requirement for SOLIDWORKS. It would only be a bonus if you do happen to have that. Currently there are a couple of different types of RAM, DDR3 and DDR4. The clock speeds for DDR3 vary from about 1333 megahertz up to about 2400, and for DDR4 it varies from about 2133 up to about 4100 megahertz. And obviously the faster the clock speed on your DDR, on your RAM, sorry, the faster it's going to work with SOLIDWORKS. So yeah, higher clock speeds are better. When you open SOLIDWORKS files, it's bringing those files into RAM. SOLIDWORKS is a RAM resident program, so whilst you're working with your large assembly in SOLIDWORKS, it's going to be in the RAM. And so the faster that you can work with those, the better your performance is going to be overall. Also note there that RAM is going to be searched before your last save location when you're looking for files. So if you're opening a large assembly file and you happen to have a part file open with the same name as a part file that's in that assembly, but it's not the same file, it's going to use the one that's in RAM before it uses the one in the last save location. If you want more information on that, you can go to the SOLIDWORKS help and look up search routine for reference documents, and it will explain to you, or go through the process that SOLIDWORKS goes through when it's checking for file locations, etc. Okay. So another consideration when you're looking at RAM is how fast are your files getting to your RAM? Where are they located? I would say that your local hard disk is going to be the best for the performance. Large assemblies that are situated on a network, you're probably better off packing and going from that network location onto your hard drive to work with them. Networks can be real bottlenecks, and depending on how many routers you've got in between you and a server, it's going to affect the kind of speeds and performance you're going to get on your local machine. We do also get a low resource warning from time to time. SOLIDWORKS has detected that your system resources are running low. It's recommended that you close some applications to free additional resources. This is not necessarily always a RAM issue, particularly on 64-bit machines. It's more often related to user objects and GDI objects, which is a Windows setting. If you're getting these types, or this type of error, it can be resolved by changing some settings in the registry, but what I would say is that if you do get that warning coming up, then it's probably best to contact us for further assistance with that issue. By and large, it's becoming less of an issue as people are switching to 64-bit and using larger amounts of memory on their system. Looking at graphics cards, my first suggestion here is don't use gaming cards, so the GeForce or Radeon type cards. Just to confuse the issue, AMD have released a new series of workstation cards called Radeon Pro. These are different from the standard Radeon cards. Okay, you can find more information at the link there about those. My personal preferences is anyway for the NVIDIA Quadro cards, quite simply because they work better with Intel CPU chipsets. I have seen issues before with the ATI or AMD graphics cards working with Intel chipsets to the point where whole systems have been replaced. So I tend to stick with Quadro, NVIDIA Quadro cards. SLI and Crossfire, this is a technology which the mid to higher range cards tend to employ to connect multiple similar cards to improve performance. SolidWorks has done some testing on these, but we haven't seen any significant performance improvements with this technology. It's probably really better on the gaming cards, and that's where they see improvements. CAD systems aren't really set up to use those technologies, so if you're thinking about using that, I'd probably be a bit wary about it, and it's probably not going to benefit you in terms of performance improvement, particularly for large assemblies. The mid to high range cards are what I'd be aiming at for large assembly modelling, the M2000 or M4000s, or the P2000 and P4000s, which are the latest cards. The M2000 and M4000 series were released last year, the P2 and P4s this year. The M and the P simply refer to the chipset that it's using on the graphics card. M is Maxwell, P is Pascal. If I switch to the next slide, I've got a table there which I grabbed off the Develop3D website, just showing the full range of NVIDIA Quadro cards there and some of the specifications. You'll see at the top end there the P5000 and P6000. You might be tempted to think they would be good for large assembly use, but actually the performance doesn't improve that greatly when using those cards, because there are some additional features that those cards have got, and SolidWorks simply just doesn't address those or utilise those additional features over the mid-range cards. The P6000 has got 24 gigs of RAM, which is probably overkill for SolidWorks anyway. The Optimus technology for laptops. This is a technology which allows two graphics cards to exist on the system at the same time. If I open up the NVIDIA display control panel, which you'll see there on the screen now, you'll know that you've got NVIDIA high performance processor if you see this option to pick a preferred graphics processor. If I drop that down, you can see I can switch between using the high performance NVIDIA processor or integrated graphics. That's an indication that you're using that Optimus technology. Just on those settings, while we're having a look, I would probably set the global preset to 3D app, regardless of whether you've got this preferred graphics processor. And then in the program settings, you can select to specify SolidWorks, bearing in mind that this needs to be installed first. If you're installing on a new system, you won't actually see that as an option. So SolidWorks needs to be installed first before you'll see that in the managed 3D settings there. And again, if you've got the Optimus technology, you'll be able to select the preferred graphics processor. If you're on a desktop with a single card, it'll just use that by default anyway. Okay, so I'll just close that off. Another thing that's probably important at the large assembly scale is order independence transparency. This was introduced for support with the NVIDIA Quadro K series using the Kepler chipset. The Maxwell and Pascal chipsets, or the M and P, should have support for order independent transparency. And basically what that does is it removes the bleed through on cards. It's a technique that can correctly render overlapping semi-transparent objects without having to sort them before they're being rendered. Again, if you're having graphics issues and are using a certified driver, please let us know and we'll take a look. You can grab your certified drivers from the video card testing link, and it will take you to a web page. There's a little preview of it there on the right hand side, where you can select your computer vendor and whether the driver status is certified and tested, and then work through those other options there to see if you can get a driver for your system. Alright, let's move on. So in terms of hard disk drives, SSDs are a must-have for improved performance generally, but critical to improve large assembly performance from a hardware perspective. SSDs are cost competitive now, so if you compare using this as a C drive compared to a large mechanical drive, you probably only need about 250 gigs to get your operating system and your program files on there, so I'd say that they are well and truly in the ballpark cost-wise. The thing that you need to know about SSD is that you need to back up your data on those drives. SSD failures are generally unrecoverable in most circumstances, so if you've got important data on there, make sure it's backed up. There are some companies that claim that they can recover SSDs. That's great, but the cost is probably prohibitive for most people. It's around about $6,000 if they do recover your data. Moving on to the SSD interface types, there are three different types. The most common is the serial ATA, which is what we showed on the system board to start off with. The transfer speed from the SSD to the CPU is probably about 6 gigabits per second, which is pretty fast, but there are some faster types. We've got SAS or SAS types, which are typically used in the data centers, which double that rate. And then we've got PCI Express, which involves putting a specialized card onto your system. And there are three different types of those. So we've got M.2 controllers. These are relatively inexpensive. They're about $100. And you go up to 20 gigabits per second across the board to the CPU. I've noticed just recently that some motherboard manufacturers are now including these on board now, and that'll help you, so you won't actually have the expense of the card to access that. Fusion I/O controllers, larger capacity and more expensive, so if you're looking at terabytes of data, you might use one of these controllers. 20 gigabytes of data, so similar to the M.2s, but they're really suited to data center usage. And then finally, the Intel Fultondale series. These are 32 gigabits per second. They're ultra fast, but they're also ultra expensive. So if you could justify the expense for whatever project it is that you're using it on, then certainly that would benefit you in terms of getting data across for large assemblies. Okay, so in terms of use of the SSD as a hard disk drive, you'd install it as your C drive. You'd probably put your operating system on there, which would be Windows. It's also the location that you'd use to run your software from, so SolidWorks in our case. And this is where you'll get the major benefit of using an SSD. Mechanical drives are still better for large volume storage of data, so you can use those for your D drive and store your files on there, but when we're running them out of memory, it's best to have your SolidWorks installed on your SSD. Okay, we will move on now. So really looking now at things that surround the hardware but aren't strictly hardware. The operating system itself, only 64-bit as I mentioned, but obviously that opens us up to using more RAM. Theoretical maximum of 16 terabytes, but I don't think there's any motherboards that can address that kind of RAM at this stage. So yeah, as I said, probably up to 32 gigs at the moment would be sufficient. Windows 7, 8.1 and 10 are currently supported, but take note that Windows 8.0 is not supported for SolidWorks 16 and 17. For Windows, we only support the professional and enterprise versions, not the home editions, but I'd suggest that if you're working with large assembly models, you're probably on professional or enterprise anyway. Antivirus exceptions. Sometimes antivirus, particularly if you're working across a network, can block, or it can check your SolidWorks parts as they're coming across from the network to your local system when you're opening them in SolidWorks. I'd probably suggest that you have your IT admins add these as exceptions. SolidWorks haven't identified any specific viruses which target those files, and so you're probably relatively safe in bringing those across as exceptions when you're opening them up. And that should improve performance, because sometimes these files will get caught up in AV systems. You won't notice it, it'll be a bit transparent, but it will actually slow down the opening process. And finally, networking in virtual environments. Really for SolidWorks and large assembly use, you probably want to think about, if you're not already using PDM as a solution to bring your large assemblies across. The reason for this is because it achieves two things. Firstly, you can store your files on a server location, but also PDM then brings those or that large assembly across locally onto your machine, so you can work at it at local speeds when you check it out. And then obviously once you've saved it and finished making new changes, you can check it back into the server and it can be safely stored there, and your IT can look after the backups of the files from there. PDM achieves a whole lot more than that, but it's in terms of large assembly use, it's certainly beneficial in that respect. If you aren't using PDM, if you're just working across a network, it's got to be Microsoft networking. Novell, Linux and NAS devices are not supported. The reason NAS devices aren't supported is because 90% of them, or 99% of them, use Linux as a base operating system on those devices. And Linux uses a different filing system to what to what Microsoft does, and the difference between those systems can result in file corruption. Similarly, cloud services are not supported or recommended for working with SolidWorks files. Cloud may be fine for storing completed projects, but I certainly wouldn't be working out of those services with live files. And I've seen issues where we've had problems working with files that simply won't save back out of SolidWorks from there, and they simply won't, or they become corrupt. So that's cloud services. And just a final point on virtual environments. They're generally not recommended for large assembly modeling unless it's specifically set up, like an NVIDIA Grid computing system. In that, I'd say that NVIDIA Grid or those types of systems are probably a separate topic in their entirety, which, if there was the call for it, we would probably cover in a webinar. So yeah, that probably closes off the bulk of what I had to say. Just one final point here. In terms of hardware, if you're looking for new hardware, IC3D, which is a sister company of Intercad as a part of the Central Innovation Group, they can provide you with hardware, so desktops, laptops, and other peripherals. If you're interested, please let me know, and I can get one of the contacts there to give you a call to further discuss what your requirements might be. These guys are also pretty well switched on with large assembly modelling and simulation requirements as well, so they really do know their stuff. I guess I'll open it up